Okay, I'm back, and we're going to look at a filter network that's intended to have a roll-off, that you have a flat gain over a certain frequency range, approximately 100 hertz to 100,000 hertz, and that it's not supposed to pass anything below approximately 100 or above approximately 100,000. Or here we go, flat between 50 and 15 kilohertz. Okay, so we come over here and we're given some facts about the input impedance. Remember that this is a model of an ideal op amp. And yeah, this would be like the feedback resistor. This would be determined by the actual feedback resistors in the op amp. This could be the R in. R out, on the other hand, could be very low, and C out. Okay. So, and these could be external components, just to make sure that we get the frequency response we want on both sides. So this would be the op amp. This would be the op amp circuit, including the feedback resistors. So we look at this situation and we say, well, what is Vn? Well, we're writing the impedance, the capacitive impedance, in terms of S instead of J omega now. And we just have resistors on the other hand. So we see that we can write the output voltage, the gain, the overall gain is output over input, and we can break that down. So we can get this output divided by this input, the source. S stands for the source input. Vn over Vs, and then Vo over Vn. How does Vo relate to Vn? So we can just figure this out. Multiply the two together and get the gain. This is just the voltage divider equation to get the relationship here. And V out, now we can use this. This becomes the voltage that's supplied to this node right here. And then this part here is the voltage divider equation for this part of the circuit. Times the voltage at that node. So we can get the second part of that gain equation and write it down. Let's see, this is Vn over Vs right here. And we rationalize it. Same thing here, Vn over Vs. Or excuse me, V out over Vn right here. These two factors. So we get the gain, the voltage gain. And multiply our stuff together. Is that 100 pi? That's 10 to the minus 3 times. Oh, and we have to invert it. That's right, invert it. The -1 up here. So yeah, this would be about 100 pi, and this would be 10 to the 7th, -7th right here, so it'd be turned into 10 to the positive 7th, and 1 over this gives you something around 10 to the -2. So you have something around 10 to the 5th, 4 times 10 to the 4th. And is that true? I'm just looking at this, looking at 1 over 0.8 is about, that just doesn't sound right, but we'll go with the exact, we'll do the exact calculations anyway. So let's go ahead and figure this out. Okay, so now I've double checked. I'm over here on new octave. The second frequency is 20,000 hertz, which is 40,000 pi radians per second. The first frequency, 50 hertz, which is a 100 pi radians per second. So it makes sense. Everything in this makes sense. I always like to double check that stuff. So make the substitutions, CRN to the -1, yeah. So you'd have to, this takes a little algebra, not much. It's just, once you know this right here, you just plug and chug. 1 over 100 pi, 1 plus the S over 100 pi, and then rationalize it. Same thing on this side. Same idea. Okay. So we have the range of S between these two extreme values. When S is between these two extreme values, we can simplify the equations. The first one, when S is going to be big, the first one's going to be 1 here. And yeah, when S is going to be big, this is going to turn into 1. This is going to go to, now it's less than 40,000. This is also going to be 1. The 40,000 dominates in this range. The 40,000 is bigger than S. So 40,000 over 40,000 is 1. S is bigger than the 100 pi. So it dominates before that. So you just get a gain of 1,000 in the mid-range. Right up here. Gain times 1,000. Watch the y-axis. You'll notice this says 1, gain times 1,000. Reality is more like the curves. Okay, yeah, and the lower frequency dominated by this curve. When S is around 100 pi or 50 hertz, somewhere in the neighborhood of 50 hertz or less. This is in the neighborhood of 40,000 hertz or greater. That's what dominates the high frequency region. Okay. Now just have some definitions here. Transfer functions, they're called. Voltage gain, we've already seen that. Transimpedance, current output, current input, voltage output. Voltage divided by current gives you an impedance. It's called transimpedance. So for op amps, transistor circuits, and the like, we define this. It has the units of ohms. Current gain, that's a bipolar transistor. So current gain, voltage gain. And then transadmittance. You put a voltage in, you get a current out. That's your transadmittance. Transfer admittance, if you will. So sometimes the voltage and current are defined at the same terminal. It's driving point, impedance or admittance. So here's an example. You have a source voltage, you have current driving from the source, you have current coming out in the output. So the transadmittance would be the I2 over V1. The voltage gain, V2 over V1. You got to solve the circuit any way you want. Transimpedance would be similar. You have an an output voltage, V2 over I1, and the voltage gain and the current gain, I2 over I1. So here's an example of same example as the last time, as the previous slide, I should say. So Thevenin's, we have let me stop here. I will pick up this example on the next video.